Yeah, that's fine. Okay, thanks so much for the invitation. So I'll be speaking today about some recent work that's we carried out in these two papers. And some people are here. So Prakash is here. So is Alexander Samposky. And so I'll be talking about G modes and their potential to uncover some compositional information in neutron stars. There is a longer version of this talk, although this talk has some updated figures. There's a longer version of this talk from an earlier conference. And if I can share my slides or submit my slides later, if you want to see some more details of the calculations and things, they're given in this recorded talk on YouTube with the link below. Okay, so just want to transmit the key ideas in this short talk. So the idea is that it's possible to get compositional information through stellar oscillations. Then there's lots of different kinds of stellar oscillations. And the focus in this talk is going to be on the G mode. And I'll explain what the G mode is, give you sort of a very basic idea of how the calculation goes and present some results. Okay, so the basic reason why G modes are interesting is that one, they couple through tidal forces to gravitational waves. So that's the observational point of contact. And from a theory point of view, basically the G modes, their frequency, their sort of scale of the frequency is set by two different kinds of sound speeds. One is the equilibrium sound speed, and the other one is so-called adiabatic sound speed. And the reason there's two sound speeds is because essentially when we talk about oscillations, we're talking about perturbations. So one can think of an equilibrium sound speed where the matter is unperturbed, and another sound speed where the matter is perturbed out of chemical equilibrium. And so the difference between these two does depend on the composition and is then reflected in the G mode. So that's the basic theoretical connection between the physics of dense matter and the composition of dense matter and the G mode. So quantifying the G mode is something that we tried to do in those two papers. And we're not the first ones, but we are the first ones to look at the effects of quark matter on the G mode spectrum. And specifically, we looked at a first order phase transition to quarks. And then I'll kind of argue that quarks seem to make quite a drastic difference to the G mode frequency. And so given that there's some potential someday to detect the G modes through gravitational waves, it might be a way to discover quark matter in neutron stars, which is kind of the holy grail for a lot of us working in this field. And then I'll present sort of a distinctly theoretical perspective on the observational outlook for G modes. So I'm not an expert by any means on waveform modeling and things like that. It's sort of there in the distant horizon for me, but I'm just going to make some simple estimates of the damping time, so you can get some idea of the observational outlook. Okay, so I'm sure you're all experts in neutron stars and you've done a lot of work on it. So just to kind of set the stage, there's different layers of the neutron star, and these layers are basically determined by the competition. At least for the crust, it's between competition between Coulomb forces and the nuclear force. And then as you get to the more denser regions, essentially you're talking about what happens to the nucleon interaction or the strong interaction at high density, which no one can really say with much confidence. So the goal is to kind of make some models for the equation of state and thereby construct the star and then try and calculate the spectrum of oscillations in the star. And essentially we're talking about core G mode oscillations. So there could be G mode oscillations in the crust. There could be G mode oscillations that are at the boundary of the crust and the core, which are called discontinuity G modes. The modes that I'll be talking about in this talk are core G mode oscillations that basically arise in the core of the neutron star. So again, that's most likely where quark matter is going to exist. So that's the one that we look at. Okay, so I won't say much about gravitational waves in this talk, but essentially that's the motivation, on the observational side. So Of course, right now we're looking at the more transient and more violent events. But as our sensitivities improve, the hope is that we can maybe detect things like mountains on neutron stars that induce some ellipticities, or fluid oscillations where the entire star is kind of vibrating for a certain length of time, and then we can hopefully detect gravitational waves from these oscillations. And if we can then make that connection that these oscillations are saying something about the composition, then we can pin down the composition. Okay, so what is the origin of the G mode? So this is sort of a basic explanation. So let's say somewhere in the core of the star, deep down, there's a bubble, and this bubble for some reason gets displaced vertically and goes upwards a little bit. So this displaced bubble can stay here if it's in mechanical equilibrium. But that means that the pressures have to be basically equilibrated, but also the densities as well. So the density is not simply a function of the pressure, it's also a function of the composition, since we're talking about non-barotropic equations of state. So basically, if this bubble goes up a little bit, it will find itself in an environment where its density is a little bit different than the surrounding density, which means that if it came from below, it will try to essentially sink back because it's overdense. And if it was displaced downwards, then it's underdense and it will try to move up. So basically, gravity acts as a restoring force to move this bubble up and down. And all this is being carried out at zero temperature, where convection effects are being ignored. So we don't consider the possibility of the bubble kind of rising continuously for any particular distance. It's just small oscillations, which we explore in a linearized limit. Okay, so the pressure is assumed to equalize fairly fast, but the density will not. So the density is a function of treated as a function of the pressure and the composition. The composition will not equilibrate very quickly. It requires beta decay reactions, which are typically longer than the time scale of oscillation. So essentially, the density is a little different. Let's call it rho star here. So we basically make a simple harmonic oscillator model and compute the characteristic vibration frequency. And doing it a little bit more carefully with the just the Euler equations. So just doing a non-relativistic version leads to a characteristic frequency called the Brun-Fiesaler frequency, which is given here by N. So it depends on the equilibrium density, the equilibrium pressure, the local gravitational field, and essentially the adiabatic index, which characterizes the equation of state. So gamma is that for the equilibrium equation of state, and this is for the perturbation. So essentially, the characteristic frequency depends on how far off equilibrium the matter is being perturbed. Now, we don't, of course, know what exactly the equation of state of the perturbation is, and it's more uncertain, let's say, than the equilibrium equation of state as well. But we can take sort of a maximally differentiated case. So we can say that the chemical composition is completely frozen out, so that essentially as this bubble moves up, it has perfect memory of what its composition was earlier. And so it has no time to change its composition. It finds itself in this new environment, it's overdense, and then it just bounces back and forth. So essentially that's going to set some kind of upper limit on how strong of an effect you can have from this kind of oscillation. Okay, so one can do, again, a more rigorous analysis using GR. Obviously, we're talking about compact stars and the cores of compact stars where GR effects are important. And it turns out not to make too much difference. So basically, you have some metric functions here borrowed from the equilibrium, the spherically symmetric Schwarzschild metric. And then you recognize here probably the combination gamma p over rho, which is basically the sound speed squared. So essentially, that's where you pick up this factor of the equilibrium sound speed. And then that with the perturbation is basically the adiabatic sound speed. So in other words, the speed of sound in matter where it's not in chemical equilibrium. So another way to think about this difference is, normally when you compute the sound speed, you have P as a function of rho from your equilibrium equation of state, and you just take let's say the numerical derivative of that along that equilibrium line. So you would get CE squared. In the literature, that's often called CS squared. So that's a little bit perhaps a point of confusion. That could be, but just for the purpose of this talk, What people normally talk of as the speed of sound in the literature is actually what we're calling here the CE squared here. But you could also take the derivative along a curve where the composition is held constant. So you'd have to kind of go on a separate curve where you don't change the composition, you only change the density. And so that gives you the CS squared here. So that difference is essentially setting the characteristic scale for the G mode frequency. Okay, so these are just the definitions. So now let's do an illustrative calculation of these two sound speeds and see how nuclear physics can enter into the problem. Okay, so this is just re-expressing these things. So dp d epsilon, P is the pressure, E is the energy density, can be expressed in terms of the neutron chemical potential. I'm assuming here we only have some nucleonic species here. And we can compute this. Let's say the simplest case is just NPE matter. And so for NPE matter, you find that you can express, you can find a relation between the two sound speeds. And CS squared is a little bit more than CE squared. And it depends on the derivative of this difference of the chemical potential. So you see here that this quantity mu tilde is basically quantifying the off equilibrium chemical potential. So essentially in beta equilibrium, this would be 0, but when you don't have beta equilibrium, then it's not. And so these derivatives are basically taken when mu tilde is not 0. And then at the end of the day, you set everything in beta equilibrium. So the order of the process matters. So you first take the derivative and then you set things to be in beta equilibrium. So when you do that, you can compute this thing. Obviously, it depends on what these chemical potentials are. So mu p, mu n, or this difference rather will depend on details of the EOS, like the potential you use and so on. Mu e, likewise, in beta equilibrium is related to the symmetry energy. So that again brings in some nuclear physics with its own density dependence. So basically, a large category of equations of state can be approximated in this parabolic form, where E of a scaled density and the proton fraction is determined by, or is given as essentially the energy per baryon for symmetric matter plus the symmetry energy times the difference here. So at x equals 1/2, basically, you just have symmetric matter, but otherwise you kind of go off of, go to asymmetric matter. So using the simple parabolic expression and some model for the equation of state, you can compute these quantities. So that's kind of the calculation we did first in this paper as a benchmark. So we chose a particular equations of state that was recently proposed by Zhao and Latimer. So you can see some of the details here. This is just one set of parameters here, and it's just representative. So you don't have to take it, 100% seriously. So for example, the maximum mass here does not meet the constraint of the 2 solar mass constraint, but again, we do have parameters that can reach that, excuse me. So basically one chooses some set of nuclear parameters that are in reasonable agreement with observations, and then computes the sound speeds. And basically what we see here, so the red curve basically shows you the difference of the sound speeds here without muons. So if it's just NPE, and then the blue curve is with muons. So the reason for calculating it with and without muons is basically to illustrate the fact that even a small change, a small compositional change, like having muons in there, which are not drastically going to change the mass or the radius of the star, does introduce a clear difference in the difference of these sound speeds. And we'll see what impact this has on the frequency as well. But this is just to show that at the moment that this new species enters, so at the moment the muon enters, the difference of the sound speed increases. So that's because you're introducing one other species in the system with its own beta decay reaction, with its own time scale. And so of course, it then becomes a little bit harder to equilibrate. The more reactions you have, you expect that it's harder to equilibrate the system. And so you expect a jump in the difference of the sound speeds. So the sound speeds themselves are relatively smooth. I haven't shown them here, but it's the difference that really drives the Brunt-Väisälä frequency and the G mode frequency. Therefore, it's the difference that matters. And it's clearly sensitive to the jump here. Okay, so there's a little bit of a jump. It doesn't look like it's much, but just hold that thought and we'll see how that develops for quark matter. Okay, so these are just some expressions we derived in the paper, but these are fairly general. So, any new species that's introduced, it could be a new baryonic species, or it could be quark matter. Anytime a new species enters, it's possible, following sort of the prescription we gave in the paper, to calculate the difference of these sound speeds here. So in the simplest case with NPE matter, one needs to know how the proton composition, how the proton fraction changes with density. If you go to muons, basically now you have a muon fraction as well as what we call as a total lepton fraction. So both of those changes will contribute to the difference of the sound speeds. So again, the impact of this jump in the sound speeds shows up in the Brunt-Weisseller frequency. So just to remind you, the Brunt-Weisseller frequency is related to the difference of these sound speeds as well as the local gravitational field. So it depends on how both of those things go. So essentially, as you have a new species coming in, you can see here that in this bottom panel where you have the muons, at the muon threshold, there's a little bit of a jump because of the difference of the sound speeds, the jump in the difference of the sound speeds. And then the overall sort of trend of the declining Brunt-Weisseller frequency is mostly driven by the local gravitational field, which decreases towards the center of the star. So the scale of the Brunt-Weisseller frequency here is essentially something like 1 to 2 kilohertz. But keep in mind, this is a local frequency. So basically, this depends on the local gravitational field and the local difference of the sound speeds. To find a global G mode, one basically has to integrate some differential equations for the entirety of the star, kind of how you would do to, let's say, calculate a love number or something like that. So there's local dependencies, but then you calculate sort of one number, the G mode frequency for the entire star. Okay, so essentially, again, this is just telling you that there's a small difference. It doesn't look like there's a big change as you go from a situation without muons to with muons, but there's still some difference. Okay, so now let's take this a step further, and our interest was to look at quark matter because that's kind of sufficiently different. You're changing, the physics in the strong interaction sector, and you're introducing, new degrees of freedom with its own interactions. So we expect that there could be some more drastic changes on the G mode as you introduce quark matter. So the motivation was also to kind of address the issue that it's quite hard to distinguish hybrid stars from normal neutron stars. I mean, this is something that Sanjay wrote a paper with Mark Alford several years ago, termed the masquerade problem. And essentially, it's not gone away. So in a recent paper, we kind of looked at a similar version of this, where we also looked at transitions to 2-flavor and to 3-flavor. So in addition to the masquerade problem, we also found what we call the camouflage problem is even if you can somehow determine that, well, you can't even say whether the transition might be to 2-flavor or 3-flavor, because you can find parameters with a suitable quark matter model that essentially mimic either case with neutron stars. So the black curve here, which is kind of hidden, is the neutron star curve, the mass radius curve. And then we tried different constructions. So we tried the Maxwell construction and the Gibbs construction for transitions from nucleonic matter to basically 2-flavor and 3-flavor matter. And in both cases, we were able to find parameters. And these two parameters basically are, you can think of them as proxies for the onset of the transition density to quarks and the stiffness of the quark equation of state. So these are typically the two things that are tuned in this class of models, which are basically quark models with some vector repulsion thrown in. So basically, one can see in either of these graphs that it's kind of, it's hard to distinguish hybrid stars from normal neutron stars on the basis of just mass and radius alone, because we can get them to be, almost identical. So with Maxwell, we did have some issues. We either, they appeared so late, the quarks appeared so late in the game that essentially the star would collapse as soon as you brought them in. But there are other models that I think Prakash and Sophia have developed that basically are able to avoid this problem. So they do get stable configurations, even with Maxwell. But basically for the Gibbs construction, we were able to satisfy all the kind of reasonable constraints, the solar mass constraint, the typical sort of radii that NICER is finding, as well as the tidal polarizability of a 1.4 solar mass star. So things that are consistent with all of the current observational constraints, but still don't allow you to distinguish between neutron stars and hybrid stars. So I think it's kind of a pressing problem that may not go away even with more precise measurements of mass and radii. So enter the G mode is, what happens to the sound speeds in a mixed phase. So again, in the paper with Simpowski and Prakash, we basically looked at how the sound speed changes when you introduce quark matter in a Gibbs construction. So essentially, this is just showing you the two sound speeds. The top panel is the two sound speeds. CS squared is the adiabatic one, CE is the equilibrium one. And essentially at the start and end of the mixed phase, you can see that throughout this, there's a difference. So the two sound speeds are almost similar because here there's no quarks. There's maybe, you can throw in muons and things, so there's a slight difference. But essentially once the quarks come in, because of the fact that you have global charge neutrality and the matter gets softer in the typical Gibbs construction, you basically have a decrease in the sound speed. And then so that kind of goes up a little bit, and then again it obviously once the phase transition is complete and you get the pure quark phase, again the two sound speeds are relatively similar. And the bottom panel shows you the difference. And if you remember the scale of the last graph where we talked about muons entering, that was about 1/10 of this. So basically the difference of sound speeds when you have something like quarks coming in is sort of a 10 times stronger effect than if you just have muons coming in. So compositional differences do matter to the G mode, and they seem to make a big difference when you have something like quarks coming in. So in this paper, we also computed some expressions for the equilibrium sound speed and the adiabatic sound speed. It requires essentially computing the phase fraction of quark matter and then knowing what the sound speeds are in the two pure phases, but then you can put them together, and then that's how we got these graphs. Okay, so again, next step is to look at the Brunt-Väisälä frequency. So again, it's just proportional to the difference of the sound speeds and the local gravitational field. So now again, you see that compared to the muons, which were a tiny blip when they entered, quarks when they entered make a pretty big difference here. So you can clearly see that at the start of the mixed phase, there's a big jump, essentially because the sound speed difference jumps. The Brunt-Väisälä frequency also has a peak. And so we expect that this should be reflected in the G mode. So basically, we can look at stars that do support quark matter and see if there's a distinctive change in the G mode frequency at the onset of quark matter. So to do that, essentially, as I said, we solve some equations in the star globally. So U and V here are just some fluid variables. So U is sort of like the amplitude of the oscillation, and V is like the pressure perturbation that corresponds to that, density perturbation. So basically the Brunt-Väisälä frequency and the difference of the sound speeds feed into this system of equations. This is done again in a what's called a Cowling approximation, where you ignore the back reaction on the gravitational potential. So normally if you were to do the full GR theory, any perturbation would also induce a change in the metric coefficients, and so you get a more complicated system. But in the Cowling approximation, you assume that the back reaction is kind of small, and it's kind of justified by some calculations that showed the difference is not perhaps more than 15% or so. Okay, so essentially what you see is that once you calculate this global G mode frequency in the star, and the three curves here are comparing quark stars, which are in brown, or strange stars, which have pure quark matter, neutron stars, which are this blue curve here, so no quark matter, although you admit muons. And then the green curve is essentially hybrid stars with the onset of quark matter corresponding to this point here. So basically, there's a very distinct jump in the G mode frequency at the onset of quarks. And this is just a reflection of the fact that this quantity n squared jumped when quarks came in. so what can we sort of deduce from this? Well, you can see that, if G mode frequencies of the order of, let's say, 500 or 600 hertz are detected, then that's a clear sign that you have to have something like quark matter or some kind of softening component in there. Because essentially, the softer you go, the higher the G mode frequency. It cannot be a neutron star because already, neutron stars are tuned to get the 2 solar mass constraint right. So this is already pretty stiff. And then if you were to make it, softer to try and get the G mode frequency of neutron stars up, you would not be able to meet that constraint. So you're already at sort of the breaking point for neutron stars with regards to how high of a G mode frequency you can get. So if you were to find something like that's distinctively, higher, 500, 600, maybe more, and you were able to conclusively say that's a core G mode, then that's a clear sign of a softening component or non-nucleonic component in neutron stars, which we interpret here as coming from quarks. Just check the time. Okay, so I'm almost out of time. So this is pretty much the last couple of slides. So in the paper, we also looked at just some estimates of, how much effect this would have on the gravitational wave phase error. So, typically, let's say you have some calculations where you compute the amplitude and the evolution of the signal in the point particle approximation, and then you include tides in there. And then, something similar, for example, was done for the tidal polarizability, and you see what sort of effect it has on the waveform. And if you get phase errors that are, of the order of 1 or so, that is perhaps, depending on the sensitivity of the detector, something that's detectable. So we again compared it for neutron stars, hybrid stars, and quark stars. The takeaway message here is that because the G mode frequency for hybrid stars is higher, that means it's excited later on in the merger, where the 2 stars are closer together, and therefore you get a higher amplitude. So you expect a higher energy being pumped, that's delta E. You expect a higher energy to be pumped into the G mode compared to just ordinary neutron stars. However, the phase error is a little smaller because, again, this happens later in the merger. So essentially, you have less time for the phase error to accumulate. So the trade-off essentially doesn't add up to something that, right now is really very promising. It appears that for the kind of frequencies that we're talking about, we need a signal-to-noise ratio of about 30 or more, which means with a single detector, we probably need an event like GW17017 that happened very, very close. But with a network or with improved sensitivities, the hope is that we can detect such events up to hundreds of megaparsecs. So in closing, I think I'll talk about the damping time, maybe if it's raised in the discussion. So let me just conclude by saying that the G mode is one kind of non-radial modes. There are others which can also be excited. And the G mode is particularly promising because it can carry the imprints of the phase of matter through these excitations. And G modes can probe stratification. So in addition to sort of having the mixed phase, one can also probe things like the crust and the core crust transition. And the oscillation modes that we computed seem to have modes that are in the frequencies that are in the observable range for LIGO, but the amplitude is probably too weak for now. And we may need sort of advanced detectors or a network of detectors. Yeah, and I hope I've sort of managed to pique your interest in G modes. There's still a lot of work to be done developing this work, and I think it's worth pursuing, especially as detectors with improved sensitivity and other detectors come online. So thank you, and I'm happy to join the discussion now.
Okay, thanks Prashanth for the interesting talk. So I see Sanjay has a question. Sanjay, please go ahead to unmute yourself.
Thanks, Prashanth. That was a very interesting talk, and especially finding ways to distinguish these new phases. I think this is certainly very promising. The question I have is about the excitation of such modes in the post-merger scenario. And have you guys looked at it, or is the temperature too high and the equilibration rate too quick so that you don't really have out of equilibrium situations?
No, we haven't really looked at that. And really nobody has. So that's sort of the next thing, is to kind of see what the effect the temperature has. But I guess in the merger, it would also be perturbed far, further off of equilibrium, which means the reaction rates would be faster. So it's possible that these modes are not, as strong, just because restoring forces would be stronger. So I don't know exactly what effect the temperature would have at this point, but it's definitely something that should be looked at.
So I mean, the basic assumption here is that the neutron star is cold enough so that any weak interaction equilibration rate is very slow compared to, like, say, the sound crossing time.
Yeah, exactly. So it's small, and then you're also assuming it's, well, one way in which the merger might be different is that, here we just use the linear approximation. So if you want to compute these things in for mergers where, the amplitudes might be larger, you might need some different approach. So we just work within the linear theory.
Okay.
Yeah.
Okay, understand. Thank you.
Yeah. Thanks, Sanjay.
Okay, so George has a question. George, please go ahead.
Hey, thank you for a very, very nice talk. My question is slightly related, I think, to Sanjay's question. So when you have the mixed phase, I mean, it seemed to me one approximation you make is that, in the sound wave, you don't really have enough time for, weak interaction equilibration to go on.
Right.
Right. So
Mm-hmm.
Is that still true, though, in the mixed phase or in the quark phase, where the masses of the weak interaction targets, entities, are significantly different? Lighter, for example.
You mean like, so you're talking about just constituent masses for the quarks?
Yeah, and I know this isn't what you have, but if I just think about, free quark gluon plasma,
mm-hmm.
I can imagine that up and down quarks have, current masses of order MeVs,
right.
The electron Fermi energy is still pretty significant in a neutron star, given that the density is high.
Mm-hmm.
So I'm just wondering whether there's a difference in the weak interaction timescales, or are they still long compared to, the inverse of the frequency?
Yeah, I think so. We didn't compute exactly the weak interaction timescales. We kind of assumed that would be the case, but there are some estimates. When I looked at the damping, for example, which, one of the sources for damping is from the bulk viscosity, which is essentially coming from the weak decay of quarks. So there we found that, well, there's a temperature factor there, but essentially we found that the timescales were still too long to essentially damp the G mode. So I looked at it in the context of the damping, but not really in the context of whether, I didn't compare it to like the nucleonic case, whether it's much larger than that or not.
Prashanth, one may add that if the quarks were completely massless, all of them, there will be no G mode from the quarks alone.
Yeah, that is true, right? So you need some compositional difference. So if all of the quark masses are zero, or if all of them are the same, which is not likely, you get essentially zero, you get no compositional changes in pure quark matter.
Very good, thank you.
Thanks.
So Wick has a question. Wick, please go ahead.
Yeah, thanks. It's a great talk. I'm pretty familiar with astroseismology and helioseismology. It's a pretty well developed field that's still getting an awful lot of investment today.
Mm-hmm.
But I know in the G modes, it's been very difficult in that field to actually identify any G mode.
Right.
It tends to be that the G mode just sort of dissipates as it gets toward lower density. And so the modeling of the dissipation in the propagation becomes really crucial. So it's been a bit frustrating. So I wanted you maybe to comment on that, and also about how would you actually detect a G, any kind of a mode in a neutron star? At least with conventional stars, what's done is to look at the Doppler shift. So you look basically at the electromagnetic signals that are associated with the motion. And the usual, I mean, they have a different precision standard, but typically their goal to try to get sub 1% sound speed inversions. They actually have to do this viewing for periods on the order of a month or more before they get the accuracy they actually need. I'm kind of wondering if you have a sense of of what might be possible. It certainly would be more limited than what one can do in a quiescent star, but can you get sound speeds to 10% in realistic scenarios? And would you use the gravitational signals associated with this, or would you also try to somehow get the angular resolution that you need to use electromagnetic signals?
Yeah, I think, I mean, it's definitely true, like compared to helioseismology, I mean, this is going to be much harder. So, I mean, for gravitational waves, essentially, all one can say at the moment is that the picture I showed regarding, if you include the coupling to the tides and you make some, well, at least there as sort of merger simulations pick up, you can have some reasonable estimate of how strong of excitation you expect in the G mode. You can look at sort of the potential, the phase change in the gravitational waveform. And right now, I don't think I can say much more than that. So certainly, I mean, this study was just focused on looking at the clear difference in the characteristic frequencies if you have a mixed phase or quark matter. But the amplitudes would probably be much more suppressed. So firstly, the F mode is the one that couples the strongest, and it takes about 80% of the energy from the tidal coupling. So you're basically working with whatever's left over among a whole host of other modes. So I think these modes would be, not very strongly excited, that's for sure. But I don't think I'm enough of an expert on sort of what's possible with, sensitivities in 10 years or something. Maybe they can pick this up, but I think it would be, electromagnetic observations. Yes, I think there've been suggestions that, for example, in gamma ray bursts, which are associated with the mergers, that these precursors could be identified with some kind of torsional modes of the crust, and essentially the estimates that one makes are pretty hand wavy at the moment. So you compute sort of a typical energy that's say pumped into the G mode, and you say, okay, let's say 10% of that somehow couples to electromagnetic flares in some way. Then one can maybe look at some constraints that way as to what the possible level of excitation is. But it's a far cry from like the precision science of helioseismology.
Very good, thank you.
I see Susan's hand is up. Susan, please go ahead with your
Actually,
question.
yeah, actually, Wick asked my question, but I guess we'll just maybe make the comment that I understood that detecting solar G modes were so very challenging, and the observations were unsubstantiated, that it's actually discussed as a potential gravitational wave target to measure with LISA, to look at the sun, to try to detect the G modes. I find this talk fascinating, but I do wonder how appreciable the observations can be. But thank you very much. I wonder, I was curious about how you would be able to calculate the amplitudes of the G mode oscillations, but as you note, it sounds very challenging.
Yeah, definitely. I think, I mean, there are some works that try to essentially model it as some kind of, resonance phenomenon that essentially would saturate, but the saturation amplitude is rather arbitrary. So, one needs some sort of nonlinear theory in order to calculate exactly what the amplitudes are. So the equations I presented to compute the G mode frequency are essentially scaled equations. So basically they don't, the amplitude can be anything. You choose some amplitude and then it basically factors out of the final result. So it doesn't give you the amplitude. So there's not much one can say other than, compute a typical energy. And then if that's sort of bounded somehow by the energy that you see in gravitational waves, then you can say something about the amplitude.
Thank you.
So any other questions or comments for Prashanth's talk today? I see no hands up. Okay, so if not, let's thank Prashanth
I
again.
just have one comment.
Okay.
I talked to Jocelyn Reed yesterday in an ECT STAR workshop about this. Asked her what are the chances. And she said, well, that will be the next generation detectors. But then she backed off saying she is not an expert at it. So I mean to talk to Nils Anderson, who seems to be very much interested in this, to see who might be an observational expert on this to follow this up a bit more. Seems to me that we have to go beyond the covering approximation, which Prashanth pointed out is rather difficult, cumbersome, if not difficult. So that's where I think one might want to go.
Yeah, I apologize that I just noticed my video is not on. I don't know. I think it switched off somehow. So I'm sorry about that. I would have to restart it to show up. So I think better not. Susan, did you still have a question, or your hand is up?
Yeah,
Sorry, I just didn't lower my hand. So
No.
sorry. So.
Okay, so yeah, other questions or comments for Prashanth? Okay, so if not, let's thank Prashanth again, and we will see you again after 2 weeks. Thank you very much today.
Thank you.
Thank you, everybody, for coming.
Thanks. Bye.
Questions. Bye-bye.
Bye.
Jilu, do you need my slides or?
Yes, if you can send your slides, yeah, to me, that would be
Okay.
great.
Okay, thank you.
Okay, thank you very much.